Welcome to Bionics of Surfaces, part 2. So what I'm interested in today is analyzing this transition, the transition between ice and water and back again, and the transition between water and gas, and what that has to do with our overarching theme of thermodynamics. So we have a whole set of problems that arise if we think about this seemingly simple process. If we look at this transition from ice to water, it can go in both directions, which is surprising. We can watch it go in both directions, and the only thing that we really change noticeably is the temperature. Going from water to gas, we can see that something slightly more complicated happens, because if we change the pressure, something interesting also happens. So let's start with this one because it's less sensitive to pressure, and then it will be slightly more simple. So starting with this transition, if we heat up our ice, if we put energy into our ice, we discover that nothing happens. That's our main use for ice, or yours, in your drinks in the summer. Put ice in the drink, and the temperature of both the ice and the drink stays at 0 degrees while energy is going into it for a while until the ice melts. So we can tell from that it takes energy to melt ice, and in chemistry we can consider that to be the energy that it takes to break the bonds inside the ice. That starts us off with our first two laws of thermodynamics. The first one is that temperature exists. So we can measure the temperature of our ice at 0 degrees, and that is a meaningful thing to do because of the first law of thermodynamics. The second law of thermodynamics says that the energy is conserved, which means if we put energy into our ice to melt it, it can't be destroyed, which means that if we cool it back down again and make ice, the energy must come back out again. So because we can observe that if we put a piece of ice in a drink and it stays at a constant temperature despite energy going in, that tells us that energy is absorbed in the process of ice turning into water, and therefore we can deduce that energy must be released when water turns into ice, which we also see if we try to make ice cream or something in the freezer. We discover it takes a really long time for ice to freeze, for water to freeze. So the time taken for water to freeze is the time that is required for the energy to get back out of the water. Okay, so what we have is heat coming out, which by convention is given a negative symbol here. So it's negative heat because it's going out into the environment from the ice, and so on the way back it's positive. Then what we can also say is that the entropy has something to do with it, because that's our next law of thermodynamics, the second law, that says that entropy exists, and it's something to do with the randomness of the universe, which we're not quite sure what is yet. But we can see that if we take something that's broadly crystalline, ice, it's usually very small crystals, but still it's broadly crystalline, we turn it into water, then we are allowing the water molecules to rotate. If they are, let's draw that. This, I'm going to have to work out a way to reflect my camera, but I can't do it. So if we take our water molecule here, there are bonds between this water and the next water molecule here, and that is in the form of a tetrahedron. So there are two bonds off the oxygen, two potential bonds off the oxygen, so there's another water here which goes away. These angles are not quite the same, but they're nearly the same. These are slightly larger, this is slightly smaller, and this crystalline structure is not super crystalline, but compared to water where the water molecules can turn around, the water liquid, where the water molecules can turn around, it is both bigger because there's space in here, and it is also much more constrained. So if we make our ice into water, we get some entropy because we've made our system more random. What that means is when we make our ice, we have to go negative, and it also means that we've got something disagreeing with the other one. Two bad things have happened to me. First of all, I made a mistake on here. I put the wrong sign on delta H there and on the top. Obviously I said the right thing, well, not obviously, but I actually said the right thing, but I wrote the wrong thing. So when heat is going out of the system, it is given the sign negative because it's going out, which is the top one. When it's going into the system, it's given the sign positive because it's going in. So when the ice's bonds break, they require energy, so it's positive. And when they give out energy, so it's negative. That makes sense, but I made a mistake. I also forgot to record the sound, so there's a little bit of a problem there. That's why I'm doing this again, and that's why my lips are moving completely randomly differently, because I'm explaining the same thing, just in a different way. What I'm now writing is the Gibbs free energy equation. The Gibbs free energy is a way of telling whether the reaction is going to go or not in the direction that we've drawn it. It is the change in energy, delta H, and the change in entropy, delta S, and there's a temperature term, capital T, in front of the delta S. So if delta G is negative, then the reaction will go, and if delta G is positive, then it won't go, which means that the combination of both the temperature and the energy of the reaction determine whether it goes or not. In the case of ice turning into water, it matters what the temperature is. So if the temperature is low, it will go in one direction, and if the temperature is high, it will go in the other direction. I'm not sure what I'm pointing at now. Okay, so this is the normal free energy equation, which you may have seen. This is a different letter, and it's a different letter because of the conditions are different. So we've got an effective temperature with entropy, an effective pressure with change in volume, and an effect of chemical energy with change in mass, so the amount of reaction. Why have I put it on this screen and drawn a bad picture of a bonfire? Because I'm talking about what we are going to keep constant. So if we have a bonfire that's an unregulated system, we could change the pressure, but it usually doesn't. But the temperature is fairly uncontrolled. The amount of fuel is fairly uncontrolled because air is going in, gases are coming out. Children throw logs on the fire. So the amount of stuff, the mass, is changing. The amount of heat, the temperature, is changing, and the pressure and volume are also changing of the actual fire. The pressure not so much in that case, but that is a real system. If we go to the chemistry system, you can see we've got much less terms, and that is because for Gibbs free energy, we are assuming that we have a fixed volume. So then the volume can't change. So the pressure is a variable, but it doesn't matter because it's fixed. The temperature is constant, but it's in the equation. So it's a T in this case. This one, the temperature is also constant, but we're changing the entropy. In the case of Gibbs free energy, we're changing the entropy, and the temperature is constant, just in here, but we could add another term for change of temperature as well. Oops, sorry, I'm putting my head out of the screen. So in our Gibbs free energy, to try to make this more clear, in our Gibbs free energy, we're assuming a container that is closed. So let's put a cork in it, and like a chemistry flask. So we've got a container that's closed, we've got our reaction mixture in there to start with, and then we set the reaction off somehow, and we can change the amount of heat that it evolves, but the temperature always returns to the starting temperature. So we have a T for temperature outside, we do the reaction, infinitely slowly, and we allow the heat to escape to the environment, or if it absorbs heat, to be absorbed from the environment, the temperature doesn't change. So I changed my mind about that, but that is the most important thing. So in thermodynamics, we assume that it takes place infinitely slowly, so the temperature doesn't actually change. What else have we got? If we change the pressure, so if it makes gas, it can't get out, so the amount of volume is not changing. And obviously if we're changing entropy inside by our ice somehow melting, for example, then it's happening inside and it's to do with the temperature. If we take the other extreme, so another part of this equation, if we take the other extreme, which would be the piston inside our car, your car, my car. We have a piston, oops, that's on behind my head. Let me rub this one out and we'll do it here, because that lens flare is in the way. So the other, no, it's behind my head, the other, and it's hard to move me. So this is a piston. We light a fire inside it. So we have some fuel, sort of an injector. We inject some fuel, we have a fire, it pushes the piston out, and now we have to have a term, which we haven't got on here, well, sort of. We have to have a term for the amount of work that this does on the environment, because that is energy, just as our heat energy was. And the only thing that's staying constant is the amount of energy. That's where this equation comes from. We assume that the amount of energy remains constant, but if we allow the volume to change, we also need a term for the work that it does on the environment, which is the volume times the change in volume, effectively, times the pressure. This term is the work that our piston is doing on the environment, so we can use that for an engine. We can use the chemistry version for chemistry. That's why I called it the chemistry version, because if we're trying to make a new chemical, we're seldom trying to extract the work, the energy from the reaction. If we're trying to model an engine, we will have to typically switch models to keep it simple, because you can see we're going to end up with a lot of terms if we also include a term for change of temperature and a term for the change of amount, because we're injecting fuel, and then we're going to end up with too many variables and not be able to solve it. So if we take an instant in time and say, in this case, the volume's not changing and no new material is coming in, so we stop time and measure that. And then we say, okay, we want to work out the work, and we let time pass a little bit with this term in, but maybe without our delta H in, because we don't want to change the temperature at the time. And then we can get a little bit more information out from our thermodynamics, but we, for the purpose of this course, are going to stick with this one. I like to mention this one because some of you will come from engineering courses and you will have seen parts of this equation. Not necessarily this particular part, but parts with this PDV term, which is the change in U. Another thing that I wanted to say at this point, this D, there are 3 Ds that we tend to use in chemistry. There is a D, which is an infinitely small amount. You use it in maths for a differential. It means it's changed by a tiny amount. And then we have to advance the equation and do it again. This is delta for a change of an actual amount. It's a Greek letter D. There's also a D. And the other D that we can have, whoops, I can't draw it backwards. It's hard for me to draw backwards. Is this one, that's from the side. It's a delta, it's a small case delta, and it is used for an actual change, but a very small one. So if we warm something up by a 1/10 of a degree, we're doing an actual change. If we warm it up by an undetectable amount, it's a D. And if we warm it up by 10 degrees, it's a delta, because we're changing the temperature. So here is our flask. It's converting into water and back again. And what we can say is, when our Gibbs free energy is going in this direction. We've got delta H, which was negative. No, it's positive because it's absorbing heat. Delta H is positive. Delta S is positive as well because it's getting more random. And our temperature is high because we're melting our ice to make water. So that will mean that this term tends to win. Oops. This term tends to win. And if we go in this direction, we can see that if we have a lower temperature, like -50, that is small, making this whole term small, which means that delta H is going to dominate. And in this direction, delta H is negative because the heat is going out. That allows us to logically remind ourselves, if we couldn't remember before, that delta G has to be negative for a process to be thermodynamically automatic, so to be preferred. That was a bad way of putting it. If it's not negative, then it will tend to go in the other direction. If it's positive, if it's 0, then nothing will happen. So we could have a temperature of 0, and at a temperature of 0, as you know from the definition of the Celsius scale, you know that water and ice stay indefinitely together. So if we took this flask and put it at a temperature of 0 outside, and there was a little bit of water and a little bit of ice, then the amount of water and ice would stay constant, but the actual molecules of ice and the actual molecules of water could change. So if we waited for a really, really long time, we would expect to see a better crystal. So the ice would melt and the water would freeze. And that would generate a new crystal of ice. So we could trace the molecules, we could label the oxygen with heavy oxygen so that we could find it, and we could work out which ones started in the water and which ones started in the ice, and they wouldn't be the same ones if we waited a really long time. Obviously, practically we can't do that. Okay, so let's take this other example. It's not a very good example because I just made it up. If we take ethane and oxygen, it takes 3.5 molecules of oxygen to make carbon dioxide and water. And we can see that it makes slightly more gas, not a huge amount more, but slightly more gas. So we have 3.5, we have 4.5 molecules on this side, one of ethane, one of ethane, 3.5 of oxygen, and we have on this side we've got 5. So we've got 4.5 on here, we've got 5 on here, so we've made more, and we've got mostly oxygen on this side, and on this side we've got mostly water, but it's a lot closer to balance, and if we have closer to balance, there are more possibilities of mixing them. So both the entropy is going up, so this is plus, and the amount of heat is negative, which in this case it makes a different reaction. The reason that I've chosen this example is, unlike water turning into ice, thermodynamically this reaction always goes forward. It's very hard to make ethane from carbon dioxide. There are ways to do it, but not just by reversing the reaction. So if we have water turning into ice and turning back into water again, it can do that just by changing the temperature. This cannot go backwards just by changing the temperature. If we take the same equation for hydrogen burning in oxygen, we see that it's not the case. If we heat up water to a high enough temperature, we get a little bit of hydrogen and oxygen. It's not very much because it makes a lot of energy, but the reaction is reversible, like the water is, like the water turning into ice is, which is not a reaction, it's a physical process. If we take, let me stop. So if we take the reaction in the other direction, whoops. If we take the reaction in the other direction, there is nothing we can do to make it happen, at least not by changing the temperature, and also not by changing the pressure, because because both terms agree with each other with the help of this negative sign in between. They both agree with each other, so there is no temperature that we can choose that makes the reaction go in the other direction. So we can define effectively two types of reaction. One where these fight against each other, and then there are temperatures where the reaction will tend to go in one direction. I keep calling it reaction, but it could be a physical process as well. If we have both in the same direction, then it will either always go or never go in that direction, whatever we do. So in this case, this reaction will always go in this direction, and it will never go in this direction on its own. If we want to make, if we want to make ethane, and we have carbon dioxide, then we have to go a long way round, taking energy and entropy from somewhere else. So to close up that, to close up that somewhat rough take of Gibbs free energy and thermodynamics, we can see in this equation we've got two parts, delta H and T delta S, and one way to think about it is that it's all about entropy. So the entropy that we're interested in is either the entropy inside the system, so we've got our flask, let me draw that again, or a box. Let's draw a box because it's square is easier. Turns out not to be. So we've got the entropy inside our system, and if the only thing that can escape our system is heat, or the only thing that can escape and go in is heat, then the only way to affect the entropy outside is delta H. So the overarching theory, the overarching assumption that we have to make is that entropy always increases, but it's the global entropy and not the local entropy, which explains both why we have these two terms. We've got the inside entropy, we've got the outside entropy, and in this case we're keeping the temperature the same, and so the temperature is only a variable here. If we take a more complicated system, like turning carbon dioxide and oxygen back into organic chemicals, we can do it, or it can be done is a better way of saying it. It can be done, but some entropy somewhere has to go up. So in that case, what usually happens is energy comes from the sun in a form of light and is converted inside plants from light into chemical energy, and it's used to force the reaction to go in the direction that it shouldn't go thermodynamically, and the gain is not heat in that case, it's light going down in value. The light has a very high intrinsic energy value, intrinsic entropy value, and it is being degraded by being turned into longer wavelength light effectively. So if we take red light, it's less entropy dense, it can provide less than blue light that has more, so it can do more, so then we can explain our situation. It also allows us to explain life. So the common explanation of why does life exist is it is a mechanism by which our planet converts the light that comes from the sun more efficiently into lower grade entropy. So effectively our planet takes in light of all kinds of wavelengths and gives out long wavelength infrared, and that is helped by plants absorbing it and giving it back out as longer wavelength light. All of the processes that we see as biology are driven by a downward slope of entropy. It's depressing, but that's how it works. Okay, so next time I think I will freeze some water and show you how it freezes. We'll try to do that demonstration experiment next time. Sorry about my hand being red. We'll try to do that demonstration experiment next time, and it will help to explain why things don't always work as they do in thermodynamics, because thermodynamics assumes that we have taken infinitely long to do things and everything has happened to the lowest possible energy, which our fourth law of thermodynamics tells us. The lowest possible energy with the lowest number of available states would be what happens at 0 Kelvin, but we might not necessarily be able to get there. And on the way there, strange things happen, which we will see. So let's do that next time.